students, I'm back with the second class on the chapter of solutions. You know, in the first video, we had discussed how we can measure the concentration of a solution in various terms such as molality, molarity, and mole fraction. So hope you have gone through that. We'll continue with the chapter of solution. And the next thing that we'll discuss today is about a liquid. You see, I have a liquid here. I've taken a liquid and this is going to be a volatile liquid. So what is a volatile liquid? You know, most of the liquid evaporates. It forms vapor. It evaporates at almost all the temperatures. So liquid starts forming vapor. Any liquid which can evaporate and form vapor just above the surface is called volatile liquid. Some liquids are less volatile and some liquids are more volatile. For example, you've got alcohol or another liquid like acetone. These liquids are highly volatile. They form vapor very quickly and in large amount. Whereas some liquids such as glycerine, you know, is less volatile. It forms very little vapor. So different liquids are differently volatile. So how do liquids exactly form its vapor? In order to form vapor, you know, the surface molecules of liquid which is on the surface must be knocked off, you know. It must be removed and taken far from the surface so that it separates from the rest of the liquid and gets converted into a gaseous state, which is known as vapor. But to knock off this surface molecule, what you need is a molecule from a bulk moving with a high velocity. You know that in a liquid, molecules move randomly. You know, some molecules move this side, some molecules move other side, and they not only move randomly, but they also move with the various velocities. You know, they've got some molecules are moving slow, so they have got less velocity, and some are moving very fast. So there are all sorts of molecules, some moving slow, some moving fast. If a fast moving liquid which has got a lot of fast moving molecule which has got a lot of kinetic energy goes and strikes a molecule on the surface, what happens? That molecule will get knocked off so far from the surface that it gets completely separated from the bulk and turns into vapor. So this is the mechanism of vaporization. This is how every liquid forms vapor. The surface molecule, when it is hit by a molecule moving in the bulk, if it's hit very hard, then it tends to go away from the liquid mass and separates and becomes vapor. This is how vapors are formed. And just above the surface of this liquid, because it is kept in open air, you've got other gases also. Like there's air here. Air has components such as nitrogen. Air also contains oxygen and lots of other gases like carbon dioxide and inert gases and even water vapor. So just above this liquid surface, you not only have this vapor of the liquid, but you've got so many other gases. Those are components of air. So if you have a mixture of gas, like we have mixture of so many gases just above the surface of liquid here, let's say you've got nitrogen gas and oxygen gas and lots of other gases in a mixture. Each gas, like nitrogen over here, exerts its own pressure, because you know that gases exert pressure. So nitrogen exerts pressure. Oxygen also exerts pressure. So all the components of this gas mixture exert their own pressure. What do you call the pressure exerted by only one component in a mixture? I'm not talking about pressure exerted by all the gases in the mixture. Only one of them. Let's say pressure exerted by only nitrogen. You know what do you call that? We call it partial pressure of nitrogen. Then what do you call pressure exerted by only oxygen? That's known as partial pressure of oxygen. So what are partial pressures in a mixture of gases? The pressure exerted by only one component gas is called partial pressure of that particular gas. So in the same manner, just above the surface of this liquid, you've got so many gases because there's air, so air has many different gases mixed together. So we've got a lot of gases here, and along with that we've got a new gas here, that is the vapor of this liquid. Now if you consider the pressure exerted by only the vapor of the liquid, not by nitrogen, oxygen, other gases, only the vapor of this liquid, that pressure is called vapor pressure of the liquid. So is vapor pressure of any liquid a partial pressure of the vapor of its liquid just above the surface? Yes, because you've got so many gases just above the surface of the liquid, and among them one of the gas is the vapor of this liquid, and whatever pressure only the vapor of the liquid exerts, which is known as the partial pressure of the vapor of the liquid, is also known as vapor pressure of the liquid. Okay, so sometimes you'll be asked to define what is vapor pressure of a liquid. So vapor pressure of a liquid is nothing but the partial pressure of the liquid, that means pressure exerted only by the vapor of the liquid just above its surface. Now how much vapor pressure a liquid has depends on the amount of vapor present here. If you've got a lot of vapor here, so naturally the vapor pressure of the liquid will be high. Some liquids which are highly volatile, which tends to evaporate a lot, will form a lot of vapor there, and therefore they have high vapor pressure. Some liquids which are less volatile, like glycerin, will form very little vapor, and therefore with very little vapor, its vapor pressure will be low. So depending on the nature of the liquid, whether the liquid is more volatile or less volatile, it will have its vapor pressure. More volatile liquid tends to have more vapor and will exhibit more vapor pressure, and less volatile liquid tends to evaporate less and exhibits low vapor pressure. Okay, so now you understand what is vapor pressure of a liquid. After learning what is vapor pressure of any liquid, now we need to focus on the factors that controls vapor pressure of any liquid. Okay, so there's a particular liquid, how much of vapor pressure it will have just above the surface of the liquid. This vapor pressure depends on many factors, and the first factor is the nature of the liquid. What's the meaning of this? I told you liquids are differently volatile. Some are more volatile and some are less. So if a liquid is there which is highly volatile, it forms a lot of vapor, and therefore it will have higher vapor pressure. So how much of vapor pressure a particular liquid exhibits, or how much vapor pressure it will have, depends on what kind of liquid you've taken. Basically, what decides the nature of this, nature like volatility, what decides that is the intermolecular forces. Like imagine a liquid which has got a very strong intermolecular force. That means liquid molecules attract each other with a strong force. In such a case, what happens, even if a fast moving molecule from the bulk goes and hits a molecule on the surface to knock it off, but because the forces between the molecules, the attraction is so strong, that liquid will be brought back, because of the strong attraction by the other molecule. And it happens because the molecules attract each other with a strong force. So it is quite difficult to form vapor in this case. Even if you strike a molecule on the surface to knock it off to form a vapor, because the molecules are attracting each other so hard that the other molecules which lies on the surface will pull that molecule back. So it tends to form vapor with difficulty. It's very difficult to form vapor in such a case. So that means if you have liquids with a strong intermolecular force, then intermolecular force, okay, strong intermolecular force, then such liquids form less vapor and will have lower vapor pressure compared to another liquid where the molecules attract each other with a very weak force. Their intermolecular force of attraction is less. So such molecules can be easily knocked off. Even a slow moving molecule from the bulk goes and strikes the molecule on the surface, that molecule can be easily sent very far from the rest. Why? Because the molecules are not attracting each other with a strong force. So with a slight push also, the molecules will easily move up and forms vapor rapidly, forms vapor very easily. Such liquid with weak intermolecular force of attraction tends to form more vapor. They are more volatile, will have higher vapor pressure. So vapor pressure formed by a liquid depends on the nature, and the nature of the liquid is decided by how strong the molecules of liquid attract each other. If the intermolecular attraction is strong, then liquid is less volatile. If the intermolecular attraction is weak, then it forms vapor very easily, so it's more volatile. So the vapor pressure of a liquid depends on the nature. The second factor that decides the vapor pressure of a liquid is temperature. You know why? Because with the rise of temperature, what happens is molecule starts moving faster, you know. Each and every molecule with the rise of temperature starts moving faster. And when they move faster, then they can easily knock off the molecule on the surface. They can easily push those molecules to vapor state compared to a liquid at a low temperature. When the liquid is at low temperature, what happens? The molecules move sluggishly. Molecules move very slow. And such molecule, even if they go and strike the surface molecule, will not be able to push them up to form a vapor. Compared to a liquid which is at high temperature, where the molecules are moving very fast, and when they go and hit the molecule on the surface, they will easily send them up from the surface, and because of that, it forms vapor very easily. Okay, so what happens to vapor pressure with the rise of temperature? Vapor pressure increases. For every liquid, vapor pressure increases with the rise of temperature. Yeah. So that's the second factor that decides the vapor pressure formed by a liquid. When the temperature increases, vapor pressure also increases. And the third one is the impurities present. If a liquid is impure, you know, what's the meaning of impurities present in a liquid? When does a liquid become impure? When you add something which dissolves in it. For example, you take pure water and add sugar, let's say, or urea, anything which dissolves in water. The moment you add a solute to a solvent, what happens? That solute goes and dissolves, its molecule spreads everywhere. For example, on dissolving sugar in water, what happens? The tiny molecules of sugar disperses itself in the liquid. It goes to every nook and corner, and some of the sugar molecule will also occupy the surface. So what is this? This is a solution of sugar and water. Is this impure? Yes, all the solutions are impure form of matter. Solutions are prepared when you mix two or more substances, you know, and when you have a mixture is never considered a pure substance. A solution is nothing but a mixture. So when I'm talking about impurities present in a liquid, I'm talking about the presence of solute dissolved in a solvent. I'm talking about a solution, because in a solution there will be impurities of solute dissolved in solvent. So once you add any impurity in a liquid, what happens? That impurity goes and dissolves and disperses everywhere. It goes to this part, that part, and it also occupies the surface. When they occupy the surface, then there will be less molecules, liquid molecules now. See, this liquid molecule, the number of liquid molecule on the surface has decreased because some of the sites are occupied by the solute or impurity particles. And now when you have less molecules of liquid, then less of them will form vapor. Earlier, you know, all of these molecules were liquid molecules, so their number was high, and because of that they could form more vapor. But now after adding impurity, some of the sites are now replaced by impurity particles like sugar particles, and because of that we have less number of molecules, liquid molecules on the surface. And when the number of liquid molecules are less on the surface, they tend to form less vapor. So what happens to the vapor pressure on adding impurity, or when you convert a pure liquid into a solution? Vapor pressure always decreases because you'll have less molecules on the surface to evaporate. Okay, so addition of impurities decreases the vapor pressure. Vapor pressure goes down. So that means a pure solvent will have higher vapor pressure compared to its solution, because in solution you have impurities, you have solute dissolved there, and solute will block those sites on the surface which can be used for evaporation. In a solution you will have less solvent molecule on the surface. Some of the sites are occupied by solute particles, and therefore when you have less liquid molecules to evaporate, they form less vapor. And that's why every solution will exhibit lower vapor pressure compared to the pure liquid or solvent. Now I'll take two liquids. Both are volatile liquids, okay? This is liquid A. It's a volatile liquid. That means it forms vapor. And it will have some vapor pressure. I'm taking this liquid in pure state, you know. This liquid A is pure. And vapor pressure of a pure liquid is represented by this symbol of vapor pressure of any pure liquid is written as P degree. Okay, and because this liquid is pure, so it's P degree, and in liquid is A, so let's say P degree A. That's the vapor pressure of the pure liquid A. Okay, and I'll also take another liquid. This one's also volatile, but this is a different liquid. This is liquid B. And different liquids are differently volatile, you know. One is more volatile and another less volatile. So it also forms its own vapor. Maybe less vapor than A or more vapor than A, depending on whether B is more volatile or less volatile, okay. So this B is also in pure state. This liquid is pure. So that's why its vapor pressure is represented by P degree. But because the liquid is B, so I'll put that suffix B. So I've got liquid A and liquid B in pure state, and their vapor pressures in pure state are P degree A and P degree B. Let me assume that I have maintained both the liquid at the same temperature, because I don't want the temperature to change, because temperature also affects the vapor pressure, you know. So both the liquids are at the same temperature. Now what I'll do is I'll prepare a mixture of both these liquids. Okay, so I'll put liquid A here, also put liquid B. So while putting liquid A and B, let me take the number of moles of A as Na. How many moles of A I've taken? In the previous video, we have talked about number of moles, how to calculate number of moles. You know, number of mole of anything is calculated by that formula. What is that formula? You've got to divide the mass of any substance by its own molecular mass. So that's how the number of moles are calculated. So while mixing A and B, these two volatile liquids, how many moles have I taken? Na moles. And how many moles of B I'll take? Nb moles. So Na moles of A and Nb moles of B are mixed together. So now this is a mixture. It's a solution of A and B. And because of that, it is impure. So over here, for A, B acts as an impurity. So because of B, the vapor pressure of A will be less. It is not going to be what it was when it is in the pure state. When it is in the pure state, its vapor pressure is P degree A. But now once it's mixed with B, B acts as impurity, and you know, with the addition of impurity, the vapor pressure decreases. So the vapor pressure of A is not going to be P degree A, it will be less. So let me write that as PA. So that's the vapor pressure of A now in this mixture. I know this much, that PA is less than P degree A. Why? Because P degree A is the vapor pressure of A in pure state. In pure state, liquid have higher vapor pressure. Whereas PA is the vapor pressure of A when it is mixed with B. So B acts as impurity. It will lower the vapor pressure of A. So A will have less vapor pressure. So PA, which is the vapor pressure in the mixture, is less than what is there in the pure state. Okay. Similarly, for B, A acts as an impurity. For B, A acts as an impurity, and because of that, the vapor pressure of B also goes down. So vapor pressure of B is now going to be, let me write PB. So that's the vapor pressure of B. Okay. PB is less than P degree B. Why? Because PB is the vapor pressure in the impure state. In impure state, vapor pressure of B will be lower, it will be less than when it was in the pure state. So PB is less than P degree B. I know that. But how much is exactly PA? I know that PA, that is the vapor pressure of A in the mixture, will be less than when it was in pure state. I know that much. It is less than. But how much exactly is PA? I don't know. Similarly, I don't know what is the vapor pressure of B over here in the mixture. So for this, we have a law called Rawl's law. You know, we have a law called Rawl's law. This Rawl's law is known as Rawl's law on binary mixture of volatile liquids. What's the meaning of binary? Binary means something which has got two components, you know, like for example, when you have a mixture of solute, one solute and one solvent, how many components in the mixture? You've got two. So when you have two things mixed together, it's called binary. When you have three things mixed together, it's called ternary. So we have a binary mixture here of volatile liquids. Both the liquids A and B are volatile. So this law, this Rawl's law, is about binary mixture of two volatile liquids. This law states that vapor pressure of any component liquid, like vapor pressure of A or vapor pressure of B, in the mixture of two volatile liquid, okay, is given by the product of the mole fraction of that liquid in the mixture and its vapor pressure in the pure state. So what's the meaning of that? Let me explain. Okay, so what's the vapor pressure of A here in the mixture? I took that as PA, isn't it? But how much is PA? I don't know. But the law says that PA, that is the vapor pressure of this liquid here in this mixture, is given by the product of the mole fraction of A. Whatever is the mole fraction of A in this mixture, you know, you understand mole fraction. Mole fraction of A in this mixture is nothing but the number of moles of A divided by total number of moles. How many moles you've got altogether? Total Na plus Nb. You've got only two components. A has Na moles and B has got Nb moles. So total number of moles is Na plus Nb. So when you divide Na by the total Na plus Nb, that gives the mole fraction of A. So I want to know what is the vapor pressure of A here in the mixture. Vapor pressure of A is given by the product of mole fraction of A and the vapor pressure of same A when it was in the pure state. So that's how you state Rawl's law on the binary mixture of volatile liquids, that vapor pressure of any one of the component liquid is given by the product of its mole fraction, its own mole fraction, not the mole fraction of B. You want to get the vapor pressure of A in the mixture, so you have to use the mole fraction of A only and the vapor pressure of same A when it was in pure state. So similarly, what is going to be the vapor pressure of B here? I know I have taken the vapor pressure of B in the mixture as PB. How much is PB then? PB is also given by the mole fraction of B, product of mole fraction of B, and the vapor pressure of B when it is in the pure state. So when you have mixtures of liquids, okay, so how do you find the vapor pressure of the first liquid in the mixture? Vapor pressure of the first liquid in the mixture will be given by the product of mole fraction of the first liquid and the vapor pressure of the first liquid when it was in pure state. Okay, so this is Rawl's law on binary mixture of volatile liquids. So let me again write the formula for the Rawl's law for binary mixture of volatile liquids. You've got two liquids mixed together, A and B. So in the mixture, what is the vapor pressure of A? Vapor pressure of A now is PA, but that is given by the mole fraction of A only and the vapor pressure of the same A when it was in pure state. Why am I rewriting this formula again? Is because sometimes you need to learn to expand this formula. What's the meaning of expanding this formula? The meaning is, suppose if they don't give you the mole fraction of A, then you need to calculate yourself. How do you calculate the mole fraction of A? Mole fraction of A is number of moles of A. Remember, we have taken Na moles of A divided by the total number of moles of both A and B. That's how the mole fraction of every component in a mixture is calculated, by dividing its own number of moles by the total. And that is also P degree A. Okay. Similarly, what is the vapor pressure of the second liquid in the mixture? The second liquid is B, so its vapor pressure is PB, is given by the mole fraction of B only and the vapor pressure of B when it was in the pure state at the same temperature. So again, when you don't have mole fraction of B given, you can find it. You know how to find mole fraction of any component. You've got to divide, for mole fraction of B, you've got to divide the number of moles of B by the total number of moles of both A and B. So that's how one can even obtain mole fractions if you don't have mole fractions given and when number of moles are given. What if the number of moles are also not given? You know, sometimes they may not give you how many moles of A you've got, how many moles of B. Then still you can find the number of moles. You remember how to find the number of moles from our previous discussion. You know, number of moles are obtained by dividing the mass of any substance by the molecular mass of the same substance. So when the number of moles are also not given, what you can do is you can expand this formula further. The number of moles of A is the mass of A divided by the molecular mass of A. Is that right? Mass of anything in grams divided by its own molecular mass gives the number of moles. So same, this is number of moles of A, which is mass of A divided by molecular mass of A. What's the number of moles of B? It's the mass of B divided by the molecular mass of B. So you can even use their masses if masses are given, if mole fraction is not given, if number of moles are not given. If you know the masses of two liquids mixed together, you can take those masses and divide by their own molecular masses to obtain the number of moles and expand this formula. So you can have a formula expanded up to this. And the same thing applies to the second one. This is the vapor pressure of the second liquid, which is when number of moles of B and A are not given. So you can do something. Mass of B, when you divide by the molecular mass of B, gives the number of moles of B, and again divide by number of moles of A. How do you get it? Mass of A by molecular mass of A. And number of moles of B, mass of B by the molecular mass of B. And then the other side you've got this one. So you can use this formula depending on what is given. If mole fractions are directly given, use this and find the vapor pressure of any liquid A or B. If mole fractions are not given, number of moles are given, then you can use this. Or even number of moles are not given, if masses are given, you can still use this formula to find the vapor pressure of any liquid when you have mixture of two liquids. Okay, so that is the first Rawl's law. The third thing that we'll do is, now what I'll do, instead of taking two different liquids, I'll only take one liquid, There's a single volatile liquid. So I need not label as A and B. I don't have two liquids. I just have one. So this is going to be a volatile liquid, It forms its own vapor. And this liquid is pure now. So this is a pure liquid. Okay. So it forms its own vapor. For pure liquid, vapor pressure of pure liquid, what we write? We write P degree. So that's the vapor pressure of this pure liquid, P degree. Now what I'll do is, I'll prepare a solution of the same liquid here by adding a non-volatile and non-electrolyte solute. What's the meaning of non-volatile solute? Solute, something which dissolves here, is a solute. A non-volatile means that solute is not going to form its own vapor. For example, if I add sugar in water, this is water, let's say this is pure liquid or pure water, and to that I've added sugar. When I add sugar, sugar dissolves here in water, but sugar will not form its own vapor. It's not a volatile substance. So I've added this non-volatile, something which will not form its own vapor. So that's the meaning of non-volatile. What's the meaning of non-electrolyte? You know what electrolytes are? Electrolytes are substances which when dissolves in solution will split, will dissociate, forming oppositely charged ions, like salts for example. When salts dissolve in water, what happens? The ions will separate. One of them forms positive ion, another forms negative ion. Any substance which dissolves and forms ions like this, positive and negative, they are called electrolytes, But my solute, whatever I have added here, is non-electrolyte. That means it's not going to split like this. It's not going to form ions. So I didn't add salt here. I added sugar. You know why? Because sugar is non-electrolyte. Now, why we are supposed to add non-electrolyte? You'll understand that later when we'll have some maturity in this chapter. After discussing few more things, you'll realize that why are we choosing non-electrolyte solute? We could have added this type of solute also like salts, but the salts goes and dissolves there and it forms ions, it splits to form ions. So we don't want that kind of solute. We want something which dissolves but does not break to form ions. Like sugar, the formula of sugar is C12H22O11. That's the molecular formula of sugar. It's a covalent molecule. So it doesn't have ions. So when it dissolves in water, it will not split to form ions. It will not break to form ions. So that's the meaning of non-electrolyte, something which does not break to form ions. So that's what I've done here. I've I've added a non-volatile solute and non-electrolyte also. It doesn't form its vapor and doesn't even break. So what happens when you dissolve sugar in water? Is it not going to turn impure? Now it's a solution. It's not a pure solvent now. It's a solution. So it's impure now. We've added impurity of sugar. So what happens to its vapor pressure? When the liquid was pure, its vapor pressure is P degree. But once you add a solute or impurity, its vapor pressure goes down. So its vapor pressure is no longer P degree. Its vapor pressure is going to be P. Okay, that's the vapor pressure of the solution. So you know that this P is less than P degree. Why? Because vapor pressure in presence of impurity will be always lowered, you know. So vapor pressure goes down. So this vapor pressure P, which is in the solution, is not going to be same as that. It's going to be less. So P is less than P degree. Okay. So this effect is called lowering of vapor pressure. So what is lowering of vapor pressure? When you have a pure liquid, it has certain vapor pressure, but the moment you add some impurity and prepare a solution, its vapor pressure starts moving down. It goes down or it decreases. And that decrease in vapor pressure because of preparation of solution is called lowering of vapor pressure. Now we can have a Rawl's law on this also. What do you call this Rawl's law? The previous Rawl's law was Rawl's law on a binary mixture of volatile liquids. Now this is a Rawl's law on the vapor pressure of a solution containing non-volatile and non-electrolyte solute. Okay, that's what we have. We have a solution here. But what kind of solution? It has got a solute like sugar, which is not volatile. It doesn't form its own vapor, and it's not even going to split into ions. So it is a non-electrolyte solute. So what does Rawl's law says? According to Rawl's law, the vapor pressure of this solution here, remember over here, this solution is vapor pressure because of the solute or because of solvent? It's because of the solvent, because solute is non-volatile, you know. So now it is the solvent which is forming vapor. Earlier also it was the solvent which is forming vapor, but then the solvent was pure. Now the solvent is not pure because we have added some impurity, that is sugar. So remember, this vapor pressure of the solution is nothing but the vapor pressure of solvent only, because it is the solvent which is evaporating, not the solute. Okay, so the vapor pressure of the solution, remember, this vapor pressure of the solution is the vapor pressure of the solvent. And how do you find the vapor pressure of any component in a mixture? From the previous Rawl's law, you know that vapor pressure of the component is given by the mole fraction of that same component. If you are finding the vapor pressure of A, you have to take the mole fraction of A. This is the vapor pressure of the solvent in the solution. Therefore, what we need is, we need the mole fraction of the solvent. In the first video, I told you that all the properties of solvent are marked as 1. Because we are dealing with a solution here, so we'll have solute and solvent. All the properties of solvent are marked as 1. That, like, mole fraction of solvent is taken as x1, and its mass is taken as w1. Its molecular mass is taken as m1. So everything about the solvent is suffixed as 1. So vapor pressure of this solution is given by the product of the mole fraction of the solvent and the vapor pressure of the same solvent when it was in pure. What was the vapor pressure of the solvent when it was in pure? It is P degree. So is it exactly like the previous Rawl's law? It is, because it is the solvent which is forming the vapor pressure in the solution also. So if you are finding the vapor pressure of the solvent, you have to take the mole fraction of the solvent and the mole fraction of the pure solvent. You have to multiply, and then you get this. So this is going to be the second Rawl's law on the vapor pressure of the solution containing non-volatile and non-electrolyte solute. So how do you state this Rawl's law? You can say that vapor pressure of the solution containing non-volatile, non-electrolyte solute is given by the product of mole fraction of the solvent and the vapor pressure of the pure solvent at the same temperature. So that is going to be Rawl's law, the second Rawl's law on the non-volatile and non-electrolyte, a solution containing non-volatile and non-electrolyte solute. So after discussing the second Rawl's law, you know, what we have found is vapor pressure of a solution containing non-volatile, non-electrolyte solute is given by the product of mole fraction of the solvent and the vapor pressure of the pure solvent at the same temperature. Remember, this is the mole fraction of the solvent. Now what I'll do is, because I've got a binary solution here, means containing solute and solvent, mole fraction of the solvent is marked as x1. So mole fraction of the solute will be marked as x2. And since you've got only two components, you know that the sum of the mole fractions of all the component in a mixture amounts to 1. Like percentages of all the components in a mixture, when it is added, gives you 100. All the percentages added together, the sum is 100. Similarly, mole fraction, all the mole fractions added together should be equal to 1. So that means mole fraction, I can take this as equation 1, okay. So mole fraction of the solvent and the mole fraction of the solute, the sum is 1. You see, why I'm writing this equation is that is because I want to replace this mole fraction of solvent there. Okay, this x1 with x2. So the value of x1 I want to replace there. So how much is x1? If you take this x2 other side, it will be 1 minus x2, isn't it? So now I'll replace this x1 here with its value, that is 1 minus x2. So I'll have p equals to x2, oh sorry, I'm replacing x2, no? Sorry, x1 as 1 minus x2, then p degree. Then let me multiply inside, p is equals to p degree minus x2 p degree. Okay? Let me take this side. This is minus, so when it comes here, it becomes plus. So x2 p degree is equals to the other side what we have, p degree, and this p goes other side and becomes negative. This goes other side and becomes negative. Now what is p degree? It is the vapor pressure of the pure liquid or pure solvent. What is p? Is the vapor pressure of the solution. So you know, let's say vapor pressure of the pure liquid, let's say p degree is 75 mm of mercury. You know, pressures are measured as the height of mercury column by barometer. So vapor pressure of the pure liquid is, let's say, 75 mm. But what will be the vapor pressure of the solution? Vapor pressure of the solution will be less, because when you add impurities, vapor pressure goes down. So P is going to be less than that. So let's say P is 65 mm. Okay, so what is this P degree minus P? Is that not 75 minus 65, which is going to be 10? This is 75, I said, I assume. This is 65, and the difference is going to be 75 minus 65, which is 10. What is that 10? Is the amount by which the vapor pressure has lowered, you know. From 75, it has come down to 65. So by what amount the vapor pressure has gone down? By 10 mm. And that 10 mm is this. This is the difference of vapor pressure. Vapor pressure of the pure liquid minus vapor pressure of the solution. This is known as the lowering of vapor pressure. This gives you the difference by which the vapor pressure goes down. So I can write that as delta P. What is the meaning of delta P? The difference of vapor pressure. This is the difference. So delta stands for difference. So delta P is the amount by which the vapor pressure has come down. Okay, so I have this x2 P degree is equals to delta P. Okay. Let me bring this here, or this one other side, you know. Let me take that. So what happens is, this side there is x2, P degree goes and divides other side. So delta P, that is the lowering of vapor pressure, the amount by which the vapor pressure has gone down, is now divided by the vapor pressure of the pure liquid. Okay. So what is this? This is the amount by which the vapor pressure has gone down. This is lowering of vapor pressure divided by the original vapor pressure of the pure liquid, you know, P degrees when it was in pure state. So lowering of vapor pressure compared to the vapor pressure of the pure liquid is called relative lowering of vapor pressure. Let me tell you what is relative. Relative physical quantities are quantities obtained in relation to others by comparing with others, you know. So we are comparing the change in vapor pressure, decrease in vapor pressure, with the original vapor pressure when it was in the pure state. That's why it's called relative lowering of vapor pressure. Okay, this quantity is called relative lowering of vapor pressure. And amazingly, relative lowering of vapor pressure of any liquid in its solution is directly equal to the mole fraction of the solute. Remember, this is not mole fraction of solvent because it's x2, this is mole fraction of solute. Okay, so what's the meaning of that? The meaning is this. Let me explain the meaning. The meaning is, you got a liquid, let's say water, pure water. It has some vapor pressure. Now you added a non-volatile, non-electrolyte solute. So the vapor pressure goes down. So the vapor pressure goes down. So that difference of vapor pressure by whatever amount it goes down is delta P. And you divide that with the vapor pressure of the pure water. So this is going to be relative lowering of vapor pressure. But how much is that going to be? That is going to be the mole fraction of the solute. So let's say I've added here 2 moles of solute. I've added 2 moles of solute with the 3 moles of water. Okay. So what's the number of moles of solute? 2 moles. And how many moles of solvent you've got? 3 moles. What's the mole fraction of the solute here? Mole fraction of the solute is going to be the number of moles of solute. How much? 2 divided by the total number of moles, that is 2 plus 3, and this is going to be 2 by 5. So because I've added impurity here, because I've added 2 moles of solute, non-volatile, non-electrolyte, its vapor pressure decreases. That decrease in vapor pressure divided by the original vapor pressure, also known as relative lowering of vapor pressure of this liquid, is going to be how much? It's going to be 2 by 5. You know why? Because look at this, relative lowering of vapor pressure of any liquid is directly equal to the mole fraction of the solute. And what's the mole fraction of the solute? 2 by 5. So this becomes third Rawl's law. The Rawl's law on relative lowering of vapor pressure. So how do you state this law? Rawl's law on relative lowering of vapor pressure of a solution containing non-volatile, non-electrolyte solute is states that relative lowering of vapor pressure of any liquid in its solution is going to be numerically equal to the mole fraction of the solute. Okay. So we're going to discuss more about the Rawl's laws, more coming properties of the solution, and more Rawl's law in the next video. Okay. So for the time being, I want to conclude the today's class here only. So keep watching the chapter of, or the videos on the chapter of solutions.